Welcome back. Today we will be starting a new chapter called Concept Generation. In fact, we will be skipping two chapters previous to that because as you know that I'm making this lecture material from this particular book that I am always citing at the end of the video, at the end of each video. So I'm skipping the in between two chapters because I feel like for us as a community it's not that important, or maybe important. You can, if you think it is you want to read it, so then you just download the book. But I just want to make it a short because it's a make the whole lecture series short, because otherwise it will be like who knows, like 3-4 or maybe 1 year lecture course, which I really don't want. Or I mean, it will go like 1 year because I post it once in a week. So, and there is like a lot of chapter, and as well as like I think like 850 plus pages of the book. So anyway, so if you want, you can read that the skipped chapters. And in fact, those chapters are okay. So I will tell you in the next slide. Yeah. So before we start, it would be good to look into the learning curve that we are going through. So I think in the second video of the lecture series, we discussed that there will be 6 phases of learning. One will be the planning, and then, I mean, in terms of, or in context to the product design and development, there will be 6 phases of learning. First phase will be about planning, and the second phase will be concept development, and this third stage or third phase will be, or phase 2, I mean, you can say phase 0 is the first stage, okay, so first phase 2 will be system level design, and phase 3 will be detailed design, and phase 4 will be testing and refinement, and phase 5 will be production ramp up. Now chapter 2 that we discussed in, I think, in the second video, there we that chapter is basically giving the glimpse of every phases, and then after that all the chapters are divided roughly into these phases. The first third chapter, opportunity identification, that is something that we discussed extensively in last 3 or 4 videos, I think. And and then there is like chapter 4, product planning, identifying, chapter 5, identifying customer needs, chapter 6, product specifications. So these 3 chapters I'm skipping, and because I believe that, you know, for us as a community, it's not like too much needed. If you want, you can read it, and also the total number of pages is like 550 or 580 or something like that. So I want to finish this book or lecture series in a reasonable amount of time, from my point of view at least, because I post the video once in a week. So today we'll be reading product specification, and upcoming then of course it's concept generation, chapter 7, concept selection, concept testing. So that's about back-to-back 4 chapters. I'm not also sure that whether I'll go into all the chapters again, but we'll see. But the main, I would say, is the main chapter, I would say, is the product architecture, and then industrial design, design environment, then design and manufacturing, prototyping, robust design, patent and intellectual property, that is important. So we'll pick up important stops from here. And try to finish the lecture series with a reasonable amount of time from my side, because I mean, from your side, of course, you can choose the video, whichever video you want to look at it, so you can do it at any time, at any pace. But for me, since I am posting it once in a week, so of course I want to finish it with a reasonable amount of time. So let's get started then. Okay, so let's get started. So the first question is, what is concept generation? So a product concept is an approximate description of the technology, working principles, and form of the product. It is a concise description of how the product will satisfy the customer needs. A concept is usually expressed as a sketch or as a rough three-dimensional model and is often accompanied by a brief textual description. The degree to which a product satisfies customers and can be successfully commercialized depends on a large measure on the quality of the underlying concept. A good concept is sometimes poorly implemented in subsequent development phases, but a poor concept can rarely be manipulated to achieve commercial success. So that's basically the reason, why concept generation and this kind of or similar sort of task is very important. Fortunately, concept generation is relatively inexpensive and can be done relatively quickly in comparison to the rest of the development process. For example, concept generation had typically consumed less than 5% of the budget and 15% of the development time in previous nailer development efforts. Because of the concept generation activity is not costly, there is no excuse for a lack of diligence and care in executing a sound concept generation method. So here in the figure you can see what is the relation of concept generation to the other concept development activities, and of course, without saying, you might have realized that concept development is a bigger topic and concept generation is part of it. So again, you'll see a lot of segmentation of various tasks and more of the executive part of it rather than technology, and I believe these are important for us also, because what you will find as a content is like a lot of discussion, and then you'll find some structured approach what can be taken. So by reading it, or to have or to keep these things in mind, will give you a safer or at least some direction that, okay, so this is the problem, or this is something that we want to develop, so how do I proceed, so that's all about the lecture series that we are doing here. So you can pick things, a lot of structured or well-tested executive methods that you can pick from here, and then you can implement on it. Not necessarily everything you have to do, but certainly you can pick whatever, because sometimes you might feel it that you are lost in whatever the process you are, and that time it's good to look back to these various things. Now, what are the things which can go wrong in concept generation and that lead to some dysfunctional concept selection, and then basically that leads to some weird product, or some product which will eventually most probably will get unsuccessful. So first is consideration of only one or two alternatives, often proposed by the most assertive member of the team. Second is failure to consider carefully the usefulness of concept employed by other firms in related and unrelated products. Third is ineffective integration of promising partial solutions. Fourth is failure to consider entire category of solutions. So again, I believe that any kind of product generation, even conceiving a bigger research projects and all these things, is all about seeing everything from a distant picture and seeing the more broader picture, macroscopic picture, and so that relates to the inter category of solution. So if you don't have the outlook from a wide angle, then you can't get the what are the structure, etc. Structured approach to concept generation reduces the incidence of these problems. A structured method also provides a step-by-step procedure for those members of the team who may be less experienced in design intensive activities. So it's good actually for example, let's say us as an individual scientist working in, let's say, maybe in academic environment, or maybe some companies also. So how do you look into the problem in a framework of a product development or product design way, so from that, if that is the problem, then we all are to some extent novice to these things. So it's good to again look into this book and get some material and what will be the structured approach at various steps that you can always copy it from here. So yeah. So the structured approach that was discussed in this book contained 5 structured steps. First step is something called clarify the problem. Second step is search externally. Third step is search internally. Fourth step is explore systematically, and fifth step is reflect on the solutions and the process. So the whole point of having a structured approach is to break the complex problem into simpler sub-problems, and then we will be using a lot of technical concepts, not like technology related or scientific concept, but like a more of an executive or management concept, like using classification tree and concept combination tables, and that will help us to systematically explore the space of solutions. So as I said that these all are actually valuable reading and learning for us, not just for any company or product development happening in the company, but even for academic researchers, especially the applied scientists. They have to come up with a bigger goal of what they want to do in research, let's say 5 or 10-year goal, and it doesn't have to be necessarily that. It can be also independent research goals, and some different people approach their research career in different way, but this can be one of the way where you have a very long duration bigger goals to achieve, and so you have given so you start with a bigger macro understanding and planning, and then you spend time and hire people, like hire PhD student, etc., and maybe other, and write projects and get securing grants and publishing papers, and so that you make your case more suitable for the next grant, etc. So in that case also, this kind of learnings will going to be very important. I'm not saying that there is no other way, but this is certainly one of the good way to see, or at least to get motivated, the structured processes, not specifically this, but like the whole thing that I'm talking about here. And many of the cases, specifically in context to concept generation, it's basically looking from a step back actually, and this is something I believe I should spend some more time on it to explain how it is very important to have a mindset of looking from a step back, because in many cases we are very much ultra focused onto simple problem, but rather our research problem, and of course this is the case for PhD students and postdocs to some extent, because they are part of a team and there is certain thing going on there, and they are satisfying the bigger or smaller medium term goal of the bigger goals that had been set by, let's say, the guide that he or she is under, PhD guide. Similarly in postdoc also, we are all part of the bigger goal actually, but when we'll go into our own research career, wherever we are, industry, academia, gradually we need to have the tell the story that this is what I stand for. Typically when you go for like some I don't know, go for some attend some lecture, not lecture but symposium, and where in generally the invited speaker, they generally give some invited talk, and in generally most of the cases they give a brief overview of presentation of the whole research that he or she is doing on his or her lab. And there you get the feeling that this person is really part of he's really showing that this is my bigger goal, and I now recently I solved this, and now I'm on this stage and various of frontiers. This is my PhD student working on that frontier, etc., etc. That's the feeling typically you'll get from this kind of lecture, and that's exactly I'm talking about that. So we need to cultivate that kind of a bigger goal and all this thing. So for that, these skills, although it looks like an executive or management skill, but then these are important, or at least one of the way one can approach the bigger problem. Anyway, so I'm not going to deviate too much into those things which are personal to some extent personal to mine, but let's focus on the learnings here. The first step is called clarify the problem, where so the input material for that particular step can be mission statement of the project, the customer needs list, the preliminary product specification. The customer need and preliminary product specification, these are basically context or the material that I haven't discussed. Actually I have skipped 2 or 3 chapters actually previous to this video, so you can always go into those things now, but anyway, so the clarify the problem step is important, and there so the mission so many design challenges are too complex to solve as a single problem and can be usefully divided into several simpler sub-problems. For example, the design of a complex product like a document copier, that means Xerox machine in general, can be thought of as a collection of more focused design problems, including, for example, the design of a document handler, the design of a paper feeder, the design of a printing device, the design of an image capture device. In some cases, however, the design problem cannot readily be divided into sub-problems. For example, the problem of designing a paperclip may be hard to divide into sub-problems. Dividing a problem into simpler sub-problems is called problem decomposition. There are many schemes by which a problem can be decomposed. Here we demonstrate a functional decomposition and also list several other approaches that are frequently useful. So in the figure you can see the first step in decomposing a problem functionally is to represent it as a single black box operating on material energy signal flow, and you can see in the first figure thin solid line denote the transfer and conversion of energy, as thick solid lines signify the movement of the material within the system, and dashed line represent a flow of control and feedback signals within the system. This black box represents the overall function of the product. The next step in the functional decomposition is to divide the single black box into sub-functions to create a more specific description of what the elements of the product might do to implement the overall function of the product. Each sub-function can generally be further divided into even simpler sub-functions. The division process is repeated until the team member agree that each sub-function is simple enough to work with. Note that at this stage the goal is to describe functional element of the product without implying a specific technological working principle for the product concept. In the figure 2, in the second figure, you can see subfunction isolate nail. This subfunction is expressed in such a way that it does not imply any particular physical solution concept, such as indexing the coil of nails into a short of or breaking a nail sideways of the stick. So these are technical terms. So it's not like a going into technical detail, but rather having a more of a step back, taking a step back and have and try to work on the higher logic. Not higher means like not better or something, but just like from the knowledge point of view. And this is, I think, is very important to learn. And yeah, the team should consider each subfunction in turn and ask whether it is expressed in a way that doesn't imply a particular physical solution principle. There is no simple correct way of creating a function diagram and no single correct functional decomposition of a product. A helpful way to create the diagram is to quickly create several drafts and then work to refine them into a single diagram that team is comfortable with. Some useful techniques for getting started are: create a function diagram of an existing product, create a function diagram based on an arbitrary product concept already generated by the team or based on a known sub-function technology. Follow on of the flows and determine what operation is required. The detail of other flows can be derived by thinking about their connections to the initial flow. So note that the function diagram is typically not unique. In particular, subfunctions can often be ordered in different ways to produce different function diagrams. Also note that in some applications the material energy signal flows are difficult to identify. In these cases, a simple list of the subfunctions of the product without connections between them is often sufficient. Functional decomposition is more applicable to technical products, but it can also be applied to simple and apparently non-technical product. For example, in an ice cream scoop has material flow of ice cream being separated, formed, transported, and deposited. These subfunctions could form the basis of a problem decomposition. Functional decomposition is only one of the several possible ways to divide the problem into simpler subproblems. Two other approaches are decompositions by a sequence of user action. For example, the nailer problem might be broken into 3 user actions. So I just want to inform you that the nailer problem, that means basically it's about creating a what is this called, a product which is basically I mean those particular machines where you can just nail, sorry, I don't know what's that exact name, but it's a cordless electric roofing nailer. Nailer means basically you just click it and then it will, so it's like a gun actually, and it will eject the nails and it will make sure that is basically stuck into that particular portion where you desire. So anyway, so that's the example, that's the part of the strategy of this book, that each chapter starts accompany some example to make the descriptions more easy to understand. So what we understand here is that the clarify the problem part. Step 1 is basically more about taking a step back approach, and then without going into the detail of the technology, you just try to divide the whole product or the potential product into various flows, like how the energy is flowed, how the material inputted, and then what material is outputted, and then of course what kind of signal. That means it can be like in case of in case of this particular nail device, it can be that triggering mechanism where you just have to what is this called, trigger, and then then the nails will come out of the machine actually. So second step is second step of the structured method is search externally. That means searching the already existing solutions of lot of sub problems that we come up with in the first step, clarify step. So we try to gather resources which already addresses the lot of problems which is we identified in this classification or clarifying part, like dividing the problem into sub problems and all these things. So external search is aimed at finding existing solutions to the both overall problem and the sub problems identified during the problem clarification step. While external search is listed as the second step in the concept generation method, this sequential leveling is deceptive. External search occur continually throughout the development process. Implementing an existing solution is usually quicker and cheaper than developing a new solution. Liberal use of existing solutions allow the team to focus on its creative energy on the critical sub problems for which there is no satisfactory priori solutions. In fact, you would like to invest your energy into doing innovation into a specific kind of a problem. And what I'm trying to mean is that by invention, if you think that all the component has to be out of the world or totally new and totally, I think that's not the way technology works actually. Most of the time it's actually have almost, let's say, 80 to 90 to 95% component, and component here can be mechanical as well as software component is same, but you'll find that 5% is actually new, and or at least concretely can be said is new, and then there you will see innovation actually. So that's how the technology works, at least that's how I understood. So for this reason, external search includes detailed evaluation not only of directly competitive products but also of technologies used in products with related sub-functions. The external search for solutions is essential an information gathering process. Available time and resources can be optimized by using an expand and focus strategy. This is important. First, expand the focus of the search by broadly gathering information that might be related to the problem, and then focus the scope of the search by exploring the promising direction in more detail. Too much of either approach will make external search inefficient. So yeah, now as far as there are at least 5 good ways to gather information from external sources. For example, lead user interviews. That means every technology or every product has some sort of lead user. It can be business to business, B2B case where the product is basically used by another business, so that's a lead user, example of lead user, or other example of lead users are available. Expert, then second is expert consultation, then patent search, that is something important for us. Literature search, that's also important. Competitive benchmarking, and that's so last I would say last 3 are more important for us, so we'll focus more into that. So search patents. Patents are a rich and readily available source of technical information containing detailed drawings and the explanation of how many products work. The main disadvantage of patent searches is that concepts found in recent patents are protected generally for 20 years from the date of the patent application, so there may be a royalty involved in using them. However, patents are also useful to see what concepts are already protected and must be avoided or licensed. That means if you want to build a new design, or so you just need to be sure that these are already protected or maybe you can license it also. Concepts contained in foreign patents without global coverage. That means we know that all the patents, there is no concept of international patent as such, like it's not like throughout the world it will be protected. Yeah, it can be in principle, but in generally when inventor or a corporation applies for patent, if they feel that this particular invention needed to be protected in this country, in generally people try to protect in US, Japan, and maybe some nowadays maybe China and European countries, various European countries, because they think that this kind of a product will be innovated or invented, or can be marketed through these companies, and those are basically in those countries. So that's how, because it's a patent application itself is a, I think is a costly process, I would say, or time, I mean time wise also is very, you need to invest a lot of time into it. Yeah, so for in further part of the lecture series, we'll dedicate into the patent and intellectual property in more detail. The formal indexing scheme for patents is difficult for novices to navigate. Fortunately, several databases contain the actual text of all patents. These text databases can be searched electronically by keywords. Keyword searches can be conducted efficiently with only modest practice, and are remarkably effective in finding patents relevant to a particular product. Copies of US patents, including illustrations, can be obtained for a nominal fee from the US Patent and Trademark Office from several suppliers. A US patent search in the area of nailers revealed several interesting concepts. One of the patent described in motor driven. So these are particularly related to the detail of the example that we are taking, but I would skip that. But we can understand that how the patent can be useful. I mean, one option is, of course, if you find certain patent to be a good solution to some of the sub problems, then you can think about license it, and you can check also that whether it's actually patented in India or not. In generally, people do not patent in India. If you find a lot of PCT application, I mean PCT numbered, patents and all these things, you'll find there are, I mean not all, but I think in European patents they have a sort of a, in the first page they mention that which countries basically these the patent had been already filed, so basically technically, as I know, I mean I'm not really sure, but what I know is like, if you file patent under PCT, that means Patent Corporation Treaty, and then you say that these are the countries where I am applying. So all these country, the patent, this patent will go to all these countries' patent office, and they will do individual survey, something like that. Most probably that's the case. But anyway, yeah, so that's about search patents. And search published literature. Published literature includes journals, conference proceedings, trade magazines, government reports, market, consumer, product information, and new product announcements. Literature searches are therefore very fertile source of existing solutions. Electronic searches are frequently and the most efficient way to gather information from the published literature. Searching the internet is often a good first step, although quality of the result can be hard to assess. More structured databases are available from online sources. Many databases store only abstract of the articles and not the full text diagram. A follow-up search for an actual article is often needed for a complete information. The two main difficulties in conducting good database searches are determining the keyword and limiting the scope of the search. There is a trade-off between the need to use more keywords for complete coverage and the need to restrict the number of matches to a manageable number. So yeah, I mean, I don't know about the specific engineering cases, but of course for basic science, of course Google and Web of Science is better, I would say, because you can do a lot of keyword search, interesting, with logical operation and all these things. So that's, I think, second topic that is important, or I feel like important for us in the external search domain. Which is second step of the concept development or concept generation that we are discussing. Benchmark related products. In context of concept generation, benchmarking is the study of existing product with functionality similar to that product under development or to the sub-problems to which the team is focused. Benchmarking can reveal existing concepts that have been implemented to solve a particular problem, as well as information on the strengths and the weaknesses of the competition. At this point, the team will likely already be familiar with competitive and closely related products. Products in other markets but with related functionality are more difficult to find. One of the most useful sources of this information is the Thomas Register, a directory of manufacturers of industrial products organized by the product type. Often the hardest part of using the Thomas Register is finding out what related products are actually called and how they are cataloged. The Thomas Register database can be accessed via the internet. For the nailer, so that's basically about the example. And so finally, to conclude, external search is an important method of gathering solution concepts. Skills in conducting external searches is therefore a valuable personal and organizational asset. This ability can be developed through careful observation of the world, to develop a mental database of technologies, and through the development of a network of professional conduct. So, even with the aid of personal knowledge and the contacts, external search remains detective work and is completed most effectively by those who are persistent and resourceful in pursuing leads and opportunities. So that's about the external search. And now we'll move into step 3, which is search internally. So next step is search internally. So search internally to means such that within your company there are like a lot of people apart from the product development team which are doing this particular task. There are a lot of people like marketing side people, can be factory people who are doing the manufacturing, etc. So they all have a certain say of a lot of thing, a lot of useful input. So so there are certain guideline one can follow when taking information from them. One is first is suspend judgment. That means don't judge their argument, whatever they are saying, just you take their take their input. Generate a lot of ideas, welcome ideas that may seem infeasible, make plenty of sketches, build sketch model. That means you can use like 3D printing, cardboard or clay depending on your product, etc, etc. And there are also like hints for generating solution concept. Can be like it's within the internal team, when the product development team are working on the problem, there can be a lot of methodologies one can apply to come up with interesting idea, like make analogies. That means okay, so this is the product, or not even the product actually, this is the sub problem, and what is the solution that people had thought about to perform the similar task, or achieve the similar goal, into the sub problem. So you will find that there is always a totally different type of product, but they used in their subsystem or sub problem, they have solved that problem. So that's the part of making analogies. And wish and wonder means like having that kind of thought, like beginning a thought of or comment with I wish we could, or I wonder what would happen if, helps to stimulate oneself or the group to consider new possibilities. So simple, basic, interesting, advices. Then distort idea. It is often helpful to modify and rearrange fragments of different solutions to create new ones. Use related stimuli, then use unrelated stimuli, then set quantitative goals, use the gallery method, etc, etc. These are if you can read it, so this is all in the book. Now something that I was interested is something called TRIDS principle. In 1990s, the Russian problem solving methodology called TRIDS, in a Russian acronym of the theory of inventive problem solving, began to be emanated in Europe and is in United States. The methodology is primarily useful in identifying physical working principles to solve technical problems. The key idea underlying treats is to identify a contradiction that is implicit in a problem. For example, a contradiction in the Naylor problem might be that an increasing power would also tend to increase weight, which is undesirable because people will be using by their hand and they will want to use one hand, so that other hand they can hold into something because they can be hanging on the roof, who knows. So one of the treats tool is a matrix of 39 by 39 characteristics with each cell corresponding to particular conflict between two. So these are details, but I think you get the glimpse of things. And so what I'm trying to say is that even in our research problems, we may not be satisfied with the existing solution that we are proposing, and that may be because the problem itself has a lot of complex dimensionality. So then you can always invoke this kind of an executive ideas that okay, so let's apply treats principle or treats methodology, how, and then depending on that how I can solve it, etc, etc. So that's about the step 3. And the next step is that step number 4 is explore symmetrically. So one approach to organizing and synthesizing these fragments would be to consider all of the possible combination of the fragments associated with each subproblem. And however, a little arithmetic revealed that the impossibility of this approach. That means there will be too many combinations. And furthermore, the team would quickly discover that many of the combinations do not even make sense. And in that context, the importance of concept classification tree and concept combination table comes into the picture. The classification tree helps the team divide the possible solution into the independent categories. Then combination table guides the team in selectively considering combinations of fragments. So that's about the explore symmetrically, and then we'll move into understanding the classification tree and combination table more detail, because that's two concepts which are important and very interesting. So the classification table you can see in the figure. So here basically you'll have like a classification, not table, classification tree, which is like just like a tree with different branches. So basically you will the concept classification tree is used to divide the entire space of possible solution into several distinct classes that will facilitate comparison and pruning. An example of a tree for the Naylor example you can see in the figure. The branches of this tree corresponding to different energy sources. The classification tree provides at least 4 important benefits: pruning of less promising branches, then the identification of independent approaches to the problem, exposure of inappropriate emphasis on certain branches, refinement of the problem decomposition for a particular branch. So that's basically our classification tree, and it's very clear that how it can really help us into dealing with a more complex product, and since it is complex product, many sub problems will be very complex, and there will be a lot of different varieties of sub problems, and you need to understand the connection between them. Then only you can think about more of a focused approach into solving the problem. Okay, so to understand the concept combination table, which is the subsequent part of after the concept classification tree, you need to understand what it means about the refinement of the problem decomposition for a particular branch. That means which is basically the help that you take out from the classification tree, or the benefit of having a classification tree. So sometimes a problem decomposition can be usefully tailored to a particular approach to the problem. Consider the branch of the tree corresponding to the electrical energy source. Based on the additional investigation of the nailing process, the team determined that the instantaneous power delivered during the nailing process was about 10,000 watt for a few millisecond, and so exceed the power that is available from a wall outlet, a battery, or a fuel cell. They concluded, therefore, that energy must be accumulated over a substantial period of nailing cycle, such as, say 100 millisecond, and then suddenly released to supply the required instantaneous power to drive the nail. This quick analysis led to the team to add a subfunction accumulate translational power energy to their function diagram. That is, you are seeing in the first figure here. They choose to add the subfunction after the conversion of electrical energy to mechanical energy, but briefly considered the possibility of accumulating the energy in electrical domain with a capacitor. This kind of refinement of function diagram is quite common as the team makes more assumption about the approach and as more information is gathered. So here you can see how the classification tree is related to concept combination table. So and then you'll have the concept combination table provides a way to consider combination of solution fragments systematically. So in the second figure here you can shows an example of concept combination table that the Taylor team used to consider the combination of fragments for the electrical branch of the classification tree. The column in the table correspond to the subproblem identified in the first figure. The entries in each column correspond to the solution fragment for each of these subproblems derived from the external and internal search. For example, the subproblem of converting electrical energy to translational energy is the heading of for the first column. The entries in this column as a rotary motor with a transmission, a linear motor, a solenoid, and a rail gun. So these are technical detail, but I think you get the idea. For example, here now you consider various boxes from each column, and if you consider solenoid, spring, and the multiple impact, then for that they come up with this design, except or this solution. Again, these are very technical, but that's the importance of why concept combination table can really help you. So that's just part of a structured approach, and I think for normal people these are very useful, I would say. Then you have when you basically consider rotary motor with transmission and spring and the single impact, then you have this kind of a design, or this is the possible way. I think I don't even understand the figures because I'm not really a mechanical engineer, but you get the idea, so yeah. Similarly, when you consider rotary motor with transmission and then spring and then multiple impact, you'll get a solution like that. Last combination here is linear motor, moving mass, and single impact, and these are the solution. Finally, so the step 5 is reflect on the solution and the process. So in matter of fact, it should not be performed throughout the whole should be performed throughout the whole process. And important questions to ask in this step, last step, is the team developing confidence that the solution space has been fully explored? Are there alternative function diagrams? Are there alternative ways to decompose the problem? Have external sources been thoroughly pursued? Have ideas from everyone been accepted and integrated into the process? So that's the step 5, and that's the last step. That's it about today's video. And next week I will start with next chapter. And yeah, so that's quite, and here of course as usual you can see this is the book I'm referring, and this is the download link also included into the description. So take care, bye bye.